Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In this lesson, we will talk about photoelectric effect, past paper question from Cambridge A2 Physics. In this lesson, you will learn how to define photon, how to define work function, and how to calculate energy of a photon if its wavelength is given. At the end of the video, we will also talk about the basic condition for the emission of photoelectrons from any metal surface. Part A1 is simply asking us what is photon. Photon is simply a packet of energy of electromagnetic radiation. This is how we can define photon. For our next question, simply we need to show that photon energy of light of wavelength 350 nanometers is equal to 5.68 times 10 to minus 19 joules. It's a quite straightforward question if we simply understand the relationship between wavelength and energy of photon. So the basic formula we need for this calculation is simply E is equal to hc over lambda. In this case, h is constant, this is Planck's constant, and c is the speed of light that is also constant. And the lambda is already given to us. We simply need to plug in values and we can calculate photon energy. This is how we can calculate photon energy. Simply in this case, as you can see here, this is value of h and this is value of c, and simply we solve this one and this is over final answer. For this question, we simply need to find the ratio between energies of two photons. One photon has wavelength that is equal to 700 nanometers and the other photon has wavelength that is equal to 350 nanometers. This question can be done by using different methods, but we will use a simple and a smart one. Let's say lambda is equal to 350 nanometers. So we can also say that 2 times of this lambda will be equal to 700 nanometers. Let's say if we need to calculate energy of this photon with the given wavelength, we can say that is E1 and that is simply equal to hc over lambda. We can also calculate energy of this photon. We can say that is equal to E2 and we can also write down that is equal to hc over 2 times lambda. Now we simply need to find the ratio between these two energies. It simply means that we need E2 divided by E1. We can also write down this one hc over 2 times lambda multiply by lambda over hc. We just need to simplify. If we simplify, these two will be cancelled and our final answer will be 0.5. For part B1, simply we need to define what is work function of the surface. It simply means that what is the minimum amount of energy required to release electron from the surface. The electron is just at the surface. How much energy we need, the minimum amount of energy. So this is what question is asking us. Now let me help you how to define work function. So this is how we can define work function. We can simply say minimum amount of energy of photon required to cause emission of electrons from surface of any metal. We need to mention surface. And also we need to understand different metals, they have different work function. As we can see here, we have 3 different metals. They have 3 different values of work function. For this question, 3 different types of metals are given to us. As you can see in this table, we have tungsten, magnesium, and potassium. Let's say the first one is tungsten and its symbol is W, and we have the second one that is magnesium. We can use also its symbol Mg just for simplicity. And the last one is potassium. We can use its symbol K. And we have 2 different types of light. Let's say the first light is this. We shine this light on all these metals and its wavelength is also given, that is equal to 350 nanometers. We shine this light on all these 3 different metals. So this is also the lambda. This is equal to 350 nanometers. Also the same light, so its lambda is also same, that is equal to 350 nanometers. Then we have another type of light and the wavelength of that light is 700 nanometers. We also shine this light on all these three metals. Now, question is simply asking us which combination will give rise to photoelectric emission. As the question is simply asking us when photoelectrons will be emitted, so we simply need to understand one very basic condition. That basic condition is simply if the energy of the photon is greater than or equal to work function of any metal, in that case there will be emission of photoelectron. So simply we need to calculate energy of each photon, we need to calculate energy of this photon, and also we need to calculate energy of second photon. If the energy is greater than work function of any metal, in that case photoelectrons will be emitted. First of all, let's calculate energy of each photon. As you can see here, I have already calculated energy of these photons. So the first photon has this much energy, that is 3.55, and the second photon has this much energy, that is equal to 1.8. As we can see here, 1.8 electron volts is less than work function of any metal. So it means in this case there will be no emission of photoelectrons. So no emission of photoelectrons. But this work function 3.55, this is greater than this one. So it means that in this case photoelectrons will be emitted. Photoelectrons will be emitted in this case from potassium metal. So one combination. But if we look at the work function of magnesium, it is 3.68 and this is greater than 3.55. So in this case, only photoelectrons will be emitted from potassium. So let me show you the final answer. So how to write the full answer. So here is how you can write the full answer. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's lesson, we will talk about photoelectric effect from Cambridge A2 Physics. In this lesson, I will explain you what is threshold frequency, how threshold frequency and work function are linked with each other, and what is the relationship between intensity and frequency of light with the help of past paper questions. Part A1 is simply asking us what is meant by the threshold frequency. Threshold frequency is a very basic concept in this chapter and we need to be very clear about this. Let me explain to you what is threshold frequency. Threshold frequency we can simply understand. Let's say we have a piece of metal and this is electron located at the surface of the metal, and a photon of light is coming, and when this photon of light reach the surface and absorbed by this surface electron, the surface electron is emitted from the surface with zero kinetic energy. So threshold frequency simply means that the lowest frequency of electromagnetic radiations we need for the emission of photoelectrons from the surface with zero kinetic energy. So often we use F0 for threshold frequency. Let's try to state what is threshold frequency. This is how we can state what is meant by the threshold frequency. So simply the lowest frequency of electromagnetic radiation we need for the emission of photoelectrons from the surface of a metal. And threshold frequency is different for different metals. The next part is simply asking us, we need to calculate threshold frequency for platinum, means is for this metal. Its work function is given to us. So how we can calculate threshold frequency? The first thing what we need to understand is that the work function of a metal is equal to the product of Planck's constant times threshold frequency. If we need to calculate threshold frequency and work function is given to us, we can simply divide that by Planck's constant. As in this case, work function is given to us, so we simply need to divide this work function by Planck's constant. And this is how we can answer this. As you can see here, I have already calculated. Very straightforward one. If simply you understand work function is equal to product of Planck's constant and threshold frequency. For part B, a continuous spectrum of wavelengths between 300 and 600 nanometers is incident on each of the metals listed in figure 7.1. These are the metals we have here. This is first metal is sodium. Its work function is given and threshold frequency is also given. Next one is zinc. Its work function is given and its threshold frequency is also given. The third one is platinum. Its work function is given and we have already calculated its threshold frequency, that was equal to 1.4 times 10 to 15 Hertz. For this question, we simply need to determine which metals, if any, will give rise to the emission of electrons. First thing what we need to understand is the basic condition for the emission of electron from the surface of any metal. So that basic condition is simply if the frequency of photon, means the frequency of incident photon, is greater than the threshold frequency of any metal, then photoelectrons may be emitted. So this is the basic condition. We simply need to calculate the frequency of photons and then we need to compare with threshold frequency of metals. If the frequency of photon is greater than threshold frequency, photoelectrons will be emitted. If it is lower than threshold frequency, photoelectrons will not be emitted. First of all, let's try to calculate frequency of each photon. So here we have calculated frequency of each photon. For this photon, its frequency we have also calculated. If we look at this frequency 1.0 times 10 to 15, this frequency is lower than frequency of platinum, because frequency of platinum we have calculated, that was equal to 1.4 times 10 to 15. But this frequency is greater than frequency of sodium and also greater than frequency of zinc. So it simply means that photoelectrons will be emitted from sodium and zinc. So this is how we can answer this question. For part C, when light of a certain intensity and frequency is incident on a metal surface, electrons are emitted. Question is simply asking us, we need to state and explain the effect on the rate of emission of electrons if we keep the intensity of the light same and we increase its frequency. It simply means that we need to understand the relationship between intensity and frequency. So let's try to understand how frequency and intensity, they are linked together. First thing we understand, intensity is equal to P over A, or we can say this is equal to energy over time times area, and E is the total energy of all the photons. We can replace this E with energy of single photon. So we can rewrite this formula. We can say this is N times E naught over T times A. So here this is the intensity, and E naught, this one is energy of single photon. So this is energy of single photon, so we can write down here. Now the next thing we need to understand is that the energy of photon is linked with its frequency. We can say E naught is equal to HF naught. HF naught. Now, if we increase the frequency of the light, mean frequency of the photon, its energy will increase. We can also say that if we increase this energy, but we are not changing the intensity, what is the effect on number of photons? So it simply means that number of photons will go down. So this is the main idea what we need to understand. If we understand this one, so we can simply answer this question. So this is how we can answer this question, and then I will explain you again why I wrote like this. So the first thing you can see here, each photon has larger energy. As you can see here, if we increase the frequency of the photon, its energy will increase. Second, fewer photons per unit time means the number of photons will decrease. And if the number of photons are less, it means less number of electrons will be emitted. So we can say fewer electrons will be emitted. Each photon will give rise to the emission of one electron. If we decrease the number of photons, number of photoelectrons will also go down. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's class, we will talk about quantum physics from Cambridge A2. We have already done 2 videos on this topic, and this is third one. For the previous 2 videos, you can go back to the channel and you can search for part 1 and part 2. In today's lesson, we will discuss what is photon, how to calculate energy of a photon, and how to calculate number of photons in a beam of light. Part A is simply asking us what is meant by a photon, and this is very common question from quantum physics, or I can simply say it's a kind of typical question from this topic. And total number of marks for this question are 2, and most of the time students, they will just get 1 mark, because they don't understand how to define in a proper way or how to write a proper answer for this question. Let me explain to you how you can write a proper answer to get 2 marks. Here is a full answer. If you write your answer like this and you mention these 2 points. First point is, if you have mentioned discrete amount of energy, you will get 1 mark. And if you have mentioned about electromagnetic radiation, you will also get 2nd mark. For part B1, simply we need to show that photon of light has energy equal to this. And let's see what is given to us about light. And about light, it is given to us that it has wavelength that is equal to 570 nanometers. Now what we need to find out, we need to find energy of photon, and we simply understand energy of photon, this is equal to h times f. F is the frequency of light, and because frequency of light is not given to us, so we need to convert this one into wavelength. So simply we understand frequency is equal to c over lambda. Now in this case, h is a Planck's constant and c is also constant, that is equal to speed of light. and lambda is given. Simply we need to plug in values and we can find out energy of a single photon. So this is how we can calculate. So in this case, simply you can see I have just plug in given values and I have done these calculations. And if you plug in lambda, so this is value of wavelength of light, and here is energy of photon in joules. You have to be little clear about this one because this is given in nanometers, so we have to convert this one into meters. If we convert into meters, our final answer will be in joules. For part B2, it is given to us that time is equal to 1.0 second, and this part is further subdivided into two parts, part 1 and part 2. It is very easy to understand for many students that the time for part 1 is equal to 1.0 second. But when students they go to part 2, they just don't know what is time. But we need to understand in this case time given for part 1 and part 2 is the same. Means all calculations for part B2 are based on t is equal to 1.0 second. This is very simple point, but most of the time this is just overlooked by many students. And so this is one thing we need to understand. Now let's try to answer this question. Now part 1 is simply asking us, we need to find out number of photons incident on the surface in 1 second. So if we read question carefully, if we go back, it is given to us that the power is equal to this 2.7 times 10 to minus 3 watts. So another way of writing this one is that is equal to 2.7 times 10 to minus 3 joules per second. Means the amount of energy incident on the surface in 1 second is equal to this one, and this is the total energy of beam arriving this surface in 1 second. And in part B1 we have already calculated energy of single photon. So now we need to use these two informations and we need to calculate number of photons. Let's try to answer this now. So if you look at this one, I have already done these calculations. So concept is very simple. First thing you need to understand, what is power? So power is rate of transfer of energy. So how we can calculate number of photons? Simply we need total energy arriving the surface in 1 second, means the total energy of beam arriving the surface in 1 second. So and we simply need to divide by energy of 1 photon. So we have total energy, we also have energy of single photon. We simply need to divide and we can calculate total number of photons. So here are total number of photons. For second part, simply we need to calculate change in momentum of the photons. But if we read question carefully, in the previous part it is given to us that the light is absorbed by the surface and light does not reflect back. So it simply means that final momentum is equal to 0. Now as we need to calculate the change in momentum, so we understand E is equal to mc square. We can little bit rearrange this one. So this is the momentum, means mass time velocity. So we can say E is equal to pc, or we can say the momentum is equal to E divided by c. So here this is momentum of a photon. E is equal to hf, so we can say this is hf over c, and this is equal to momentum of photon. And f over c, we simply understand this is equal to 1 over lambda. So we can say momentum of a photon, that is simply equal to h over lambda. So here you can see we have just plug in value of h. H is Planck's constant, and this is value of lambda of light. And if we just solve it, we can find momentum of single photon. But in this case, the number of photons arriving the surface, they are equal to this. And we need to find the total change in momentum. So we just need to multiply number of photons with momentum of single photon. So this is the final answer, mean this is the change in momentum. For part C, simply we need to use our answer in B2 and we need to calculate pressure exerted by the light on the metal surface. Pressure, we simply understand this is equal to force over contact area, or simply we can say over area. So force also we understand that is equal to rate of change of momentum. We can say simply delta P over delta T. And delta P over delta T we have already calculated in part B2. So it simply means that we need to divide part B2 by area of the surface and we will be able to find pressure. So as you can see here, first of all, I have written that pressure is equal to force over area, and then force we can say is equal to change in momentum per unit time, and then we have to divide by area. And this is our answer from part B2. We simply divide it by contact area, and this is our final answer. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's class, we will talk about quantum physics past paper question. In this lesson, I'll explain you how to calculate momentum and energy of a photon. And also, I will explain to you how energy is conserved when a photon is incident on an electron, and how to calculate angle between deflected photon and electron. For this question, it is given to us that a photon is incident on an electron and electron is initially just sitting here, means its initial velocity is equal to 0. And this is given in the question here. After this photon collide with electron, photon is deflected at certain angle, and angle is also given here. Wavelength of deflected photon is given and wavelength of incident photon is also given. If we compare the wavelength of deflected photon with wavelength of incident photon, we will simply see that the wavelength of deflected photon is greater than wavelength of incident photon. We also understand energy of a photon, that is simply equal to hc over lambda. So from here we can conclude that energy of incident photon is greater than energy of deflected photon. So it simply means that incident photon has lost some energy, and that energy has been transferred to this electron. And if we look at this overall setup, simply we can understand is that it is like two particles, they are colliding with each other. One particle is gaining kinetic energy and one particle is losing energy. And this whole setup is called Compton scattering experiment. This experiment showed that light behaves as a particle. Now let's try to answer part A now. For part A, simply we need to calculate momentum for the incident photon. Momentum we understand simply is equal to h over lambda, and h here is a Planck's constant and we can find out from data table. And lambda is wavelength of incident photon. We simply just need to plug in these values and we can calculate value of momentum. So here you can see I have just plugged in values of Planck's constant and wavelength. And here is our final answer. For this part, simply we need to calculate energy of incident photon. It simply means we need to find energy of this photon. And for this photon, its wavelength is given to us and energy is simply equal to hc over lambda. So this is lambda of incident photon. So h is constant, this is Planck's constant, c is also constant. We simply need to plug in value of these quantities and we can calculate energy of incident photon. Quite straightforward one. So if we plug in values of h and c and lambda for incident photon, then this is energy of incident photon. For part B, question is simply asking us, we need to calculate the value of angle theta. And it is a formula is given to us. If we look at this one formula, everything is given to us. We simply need to plug in values. Delta lambda, that is given to us. This is the change in wavelength of the photon. H here is the Planck's constant and c is the speed of light in free space, and me, this is mass of electron. Me is mass of electron, so this is also given to us. Me is mass of electron, and this also we can find in data table. Now simply what we need to do is we just need to use this formula and we need to plug in values of all these quantities, and then we will be able to find value of angle, this angle theta. Now just plug in values and find answer. So here you can see I have already done these calculations, and you can see here after calculations I have found this is our final value of theta. And this lambda, this is actually lambda of deflected photon, that is given here, lambda of deflected photon, and here is lambda of incident photons. So this is lambda of incident photon. If we plug in values, we will get our final answer, and this is value of theta. Now let's move on to second part now. For the second part, we need to use energy considerations to suggest why delta lambda must always be positive. So this is simply based on energy conservation, and the hint is also given to us here. We need to use energy considerations, mean we have to answer this question based on conservation of energy. As we have already seen here, when this photon, means this incident photon, when this will collide with this electron, electron will gain some kinetic energy. So in this deflection, a photon is losing energy and electron is gaining kinetic energy, so the energy of photon will decrease. And when energy of photon decreases, its lambda has to increase. As we simply understand, E is equal to hc over lambda. If energy of photon goes down, lambda has to increase. So lambda increase, it simply means that lambda of deflected photon will always be greater than lambda of incident photon. So we can simply say delta lambda will always be positive. So this will always be positive. So here is our final answer. So this is how you need to write answer. So simply you need to say that during the deflection, electron also get deflected and electron gain some energy from the photon. So deflected photon has less energy, and therefore deflected photons has longer wavelength, and that's the reason change in lambda is always positive. Just you need to use law of conservation of energy. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's class, we will talk about quantum physics past paper question. And this is fifth video on this topic. In this lesson, we will explore more concepts from this chapter with the help of past paper questions. For this question, it is given to us that light of wavelength lambda is incident on a metal surface and work function of metal surface is given, that is equal to phi. And photoelectrons of maximum kinetic energy, here E max is used for maximum kinetic energy. Photoelectrons are emitted from the surface, so it simply means we just need to focus on photoelectrons emitted from the surface. So let's try to understand, let's try to sketch this one so we can see a clear picture of what is happening. So this is our piece of metal. You can simply imagine that this is a piece of metal and light is incident on this piece of metal. As it is given in the question, the wavelength of this light is lambda and light consists of photons. We can also draw this small box here to show that photon is a packet of energy of electromagnetic radiations. Now, as in this question, simply we need to focus on emission of photoelectron from surface. So we can also draw these small circles to show that these are electrons at the surface. So as these photons are absorbed by these electrons, so one photon will give all of its energy to one electron. This is one-to-one interaction, and as soon as this photon is absorbed by this electron, electron will be released from a certain atom. So electron will use some of its energy to release itself from the atom, and the remaining energy of electron will become its kinetic energy. As electron is released from the surface, so this is the maximum kinetic energy possible. If we use this light and we have this metal, so that will be maximum kinetic energy possible. In question, they're using E max. Actually, this is kinetic energy maximum of photoelectrons. So in this case, let's try to understand a little bit in a proper way. So first of all, we have photon. So photon has certain energy. We can say photon energy. First of all, this is used to release electron from a certain atom. So this is the minimum energy, and this is called work function. So we can also write down here, this is work function, minimum amount of energy required to release electron from a certain atom or from certain metal. And the remaining energy is converted into kinetic energy of photoelectron. So this is kinetic energy of photoelectron, kinetic energy maximum of photoelectron. So here we have photon energy. So this energy, photon gives all of its energy to single electron, and single electron first of all use some of energy to release itself from the metal or from a certain atom, and remaining energy become its kinetic energy. Now, in this case, we have to use principle of conservation of energy, and we need to write an equation. So let's try to write down an equation now. So first thing, we need to understand what is photon energy. If the wavelength of light is given to us, we can simply write down that is hc over lambda. Work function is already given to us. Kinetic energy maximum, so this is simply we need to use symbol E max. We can simply write down here that energy of photon, this is equal to work function plus this is equal to kinetic energy maximum of photoelectron. Question is also asking us, explain any other symbols you use. Mean other than these three symbols, these quantities, if we use any other symbol, we also need to explain. In question, lambda is given to us, phi is given to us, E max is also given to us. But we use these two new symbols. We also need to tell what are these symbols. Planck's constant, so this one is simply Planck's constant, so we have to write down what is this h. And c, this is speed of light in vacuum, this is also constant, so this is speed of light in vacuum. We also need to explain this one. If we have written all these things, we will get 2 marks. This is all what you need to explain for part A. For part B, the variation of 1 over lambda with E max is given. E max is given on y-axis, and this is kinetic energy maximum of photoelectrons. On x-axis, we have 1 over lambda, and this is wavelength of light, means incident light. So this is wavelength of light. Question is simply asking us, we need to use our answer in part A, and we need to explain why the gradient of the line does not depend on the metal surface. Why, simply we can say why this gradient is constant for different metals. Now, in order to answer this question, simply we need to use our answer in part A. In part A, simply we have written that Hc means energy of photon. This is equal to work function plus this is E max, kinetic energy maximum of photoelectron. Now we just need to rearrange this one. If we little bit rearrange this, we can simply write down E max is equal to Hc times 1 over lambda and minus phi, this is work function. Now if we compare this one with straight line equation, y is equal to mx plus c, we will simply find out that gradient of this graph, that is equal to hc. We will simply say gradient is equal to hc. M is the gradient, and 1 over lambda, this is x, and y-intercept negative, y-intercept, this is phi, and Emax is on y. So this is all we have. So if we look at this one, we have gradient that is equal to hc. H is a constant, c is a constant, so these two are constant. Gradient is depending on these two constants. That's the reason the gradient is constant for different metals. Now let's try to write down answer. So this is how we can write our final answer. Simply we need to write down that the gradient of the graph, this is equal to hc. H and c, they are constant. So that's the reason gradient is independent of metal surface. For this part, it is given to us that work function energy of sodium is equal to 2.28 electron volts and E max is 0, means the kinetic energy maximum of photoelectron is 0. This is also given to us. what we need to find out, simply we need to find out minimum wavelength. We need to find, for this question we need to use Einstein equations of photoelectric effect, and that equation we have already discussed in part A. So we can write down again here, that is equal to Sc over lambda, mean this is energy of photon, and this is equal to work function plus kinetic energy maximum of photoelectron. And in this question it is given to us that kinetic energy maximum, that is equal to 0. So simply we can say that Hc over lambda, this is equal to work function. And what we need to find out, we need to find out this lambda naught, means the minimum wavelength of incident light we have to find. So in this case, H is constant, C is constant, these we can find out from data table, and phi is given. So this is work function, this is given to us, but this is given in electron volts. So we need to convert this one into joules first of all. So this is a key point. We need to convert this one into joules, and then we can plug in values in this formula, and we can find out lambda naught, mean minimum value of wavelength we can find out. So you can see here I have done this question already, and concept is quite simple one. As I mentioned before, Emax is 0, this is given in question, so Emax is equal to 0. So this is our equation now, and in this equation we need to plug in values. Work function energy that is given, we need to convert into joules, so we multiply with this one to convert this one into joules, and this is value of H, and this is speed of light in vacuum, and we can find out lambda naught, lambda minimum. Welcome to A-Level and AP Physics, a place where you can improve your understanding of physics with confidence. In today's class, we will talk about quantum physics past paper question, and this question is very important because this question is very common on A-Level exams. In this lesson, I'll explain to you what is threshold frequency and when kinetic energy of photoelectrons is maximum, and how to sketch a graph between kinetic energy maximum and 1 over wavelength. Part A is simply asking us, we need to explain what is threshold frequency. Threshold frequency simply means that, let's say we have a piece of metal and we shine light on this one, and let's say electron is emitted from this surface, and this electron has no kinetic energy, mean just emitted from the surface and just sitting here. So the frequency of this electromagnetic radiation, then we will call this is threshold frequency, and this frequency is the minimum frequency of electromagnetic radiation we need for emission of electrons from a metal. So that minimum frequency is called threshold frequency. This is how you can write your answer. So in answer you can see I have written here minimum frequency. So minimum frequency is very important. You have to mention minimum frequency of incident electromagnetic radiation to cause emission of electrons from a metal surface. And threshold frequency depends on metal surface. If we change the metal, threshold frequency will change, means we need different frequency of electromagnetic radiation for emission of photoelectrons with zero kinetic energy from metal surface. Part B is simply asking us, we need to explain why the emitted electrons have a range of values of kinetic energy below a maximum value. It simply means that if we have a metal surface and we shine light on this, electrons will be emitted from this metal surface if the frequency of electromagnetic radiation is greater than the threshold frequency. Means if frequency of electromagnetic radiation is greater than threshold frequency, electrons will be emitted from the surface. Let's say this electron is emitted from metal surface and the kinetic energy of this electron, let's say, is equal to 600 electron volts. Another electron is emitted from below the surface and kinetic energy of that electron, let's say, is equal to 500 electron volts. Now in this case you can see these electrons, even they are emitted from the same surface and same light is shining on the surface, but these photoelectrons, they have a range of kinetic energy. So this is what we need to explain, and this simply we can explain based on law of conservation of energy. So we can simply write down equation for conservation of energy. So this is energy of coming photon and this energy is absorbed by electron. And so the first one is the work function, means electron will use this energy to release itself from atom. And then here is the kinetic energy of electron, photoelectron, and plus electron also has to do work against attractive forces if electron is released from below the surface. So attractive forces, simply means that these are the forces between electron and ion, because electrons negative, ions positive. So attractive forces, if electron is coming from below the surface, electron has to overcome these attractive forces, or simply we can say electron has to do work against these forces to reach the surface. So that work done to reach the surface is here. Now if electron is emitted from the surface, then this one will be 0, and then this kinetic energy will be maximum possible kinetic energy of that electron. And other electrons emitted from below the surface, they will have different amount of kinetic energies depending on from where they are coming, or simply we can say depending on that. So this is all what we need to understand. If we have this clear understanding now, so we can write down our answer. So here is our final answer. As you can see here, now I have written this one for you, so you can just see. Now here is our final answer. You can see only the surface electrons, they will have kinetic energy maximum. The emitted electrons from different depths inside the metal, they have different amount of energy because they have to overcome the surrounding bonds, or simply we can say they have to overcome the attractive forces, or they need to do work against attractive forces to reach the surface and escaping with the remaining kinetic energy. As WF we have already mentioned. So they have low kinetic energy compared to the surface electron, and for surface electron we say they have kinetic energy maximum. For part C, simply we need to understand this graph. As you can see here, on y-axis we have kinetic energy maximum, and on x-axis we have 1 over lambda. Part C1 is simply asking us, we need to use figure 7.1 to determine the threshold frequency without reference to the work function. It simply means that we need to use this graph and we need to find out threshold frequency. At threshold frequency, this is the minimum frequency of electromagnetic radiation we need for emission of electrons when kinetic energy maximum of electron is equal to 0. Kinetic energy maximum is equal to 0. It simply, this one is telling you, you need to extend this line and this line will intersect this axis. So at here, if when it intersects x-axis, it means the kinetic energy will be equal to 0, and at that point you can find value of 1 over lambda, and then we can use this equation F naught is equal to C over 1 over lambda naught. So from here here we can find out value of threshold wavelength we can find out. So we can find out threshold wavelength. I can write down threshold lambda you can find, and then you need to use this equation and you can find out F naught. So as you can see here now, I have already drawn this line for you. So from this line, we have determined value of threshold wavelength. As you can see, 1 over lambda naught, this is equal to this. And we just plug in values, and this is over value of threshold frequency. Now the next question, C2, is asking you use your answer in 1 and calculate work function energy. And work function energy, we simply understand work function is equal to h f naught, and this is the threshold frequency. Now simply we need to plug in this value here, and h is a Planck's constant, and we will get our answer for work function. So here is our final answer, and this is how you can do these calculations. So this is our final answer for work function. We simply use this formula. That's all. This question is simply telling us cesium metal has a work function energy, means the work function is given to us on the axis of figure 7.1. This is figure 7.1. Sketch a graph to show the variation with 1 over lambda of Emax for certain metal. So if we write Einstein's photoelectric effect equation, HF, this is equal to work function plus we can say this is kinetic energy maximum. We can rearrange this one. We can bring kinetic energy maximum on one side, and we can write down HF. So we can also write down this is like this. HF you can replace with HC over lambda minus work function. Now in this case, let's say we compare this one with straight line equation, y is equal to mx plus c. This is mx plus c. Now you can see 1 over lambda, this is actually is x, and hc, this is the gradient of the line, and this is gradient. In this case we can simply write down gradient is equal to hc. H is a constant, c is a constant, so it simply means that gradient is always constant. It is not depending on metals. Even we change the metal, gradient will be constant. So simply we can say that gradient is constant. Now we understand the gradient of the new line also has to be the same, means two lines have to be parallel. As you can see, work function is given to us. We can calculate first of all 1 over lambda. When we have value of 1 over lambda, so it will intersect somewhere here, and we will draw another line. So let me show you how to draw that line. So this is how you need to draw the line. So this is for part D. So this line you need to draw. So what we have done here, we have calculated first of all 1 over lambda, and then we just need to draw a line parallel to the previous line. That's all.